we can examine the behavior of a system of particles by treating the system as if all the mass is located at the center of mass of that system. And we can use conservation of momentum on the overall system of particles to do that. You think about this cat as our system of particles, and as you drop it, it's twisting around and doing whatever it's doing. But we notice that the center of mass of the cat is falling, and just like a particle would fall, regardless of whatever is happening with the rest of the particles involved in our system. If we consider maybe a little bit easier to understand system with 3 discrete masses here, we can try and find the center of mass of that system following this process laid out in the course text that'll point you to if you want to see that, where our total mass is equal to the sum of all of those masses. So far, no surprise, m1 plus m2 plus m3. And then the position of our center of mass is now given by 1 over that total mass times the sum of our mass times our position of each mass. In component form, you can do this and do this separately for the x, the y, and the z directions. Graphically, I think this kind of helps see what's going on. We start by weighting each of these positions by how much mass is there. So mass 1 times position 1, mass 2 times position 2. Note here that mass 2 must weigh less than mass 1 because the weighting makes this resulting vector less. And then mass 3 times position 3. We then add those vectors. That's this summation notation here. We do a vector sum. You can think about that as adding tip to tail here. So graphically that looks like m1r1 plus m2r2 plus m3r3. And our resultant vector is that m1r1 plus m2r2 plus m3r3. We then multiply by 1 over m, or divide by the combined mass, and we get our position of our center of mass as being right there. That's finding the center of mass of discrete points. If you want to do that for a continuous distribution of mass, you can do the same thing. It's just instead of adding up the discrete bits of mass, this will become an integral sum. As shown here, our total mass can also be an integral sum of the little bits of mass, and our position of the center of mass now is 1 over the total mass times the integral of r dm. And that lets you deal with, for example, a ring of mass going around the ring. You can integrate that to find the total mass, and then you can integrate r times dm to get your integral here, and then divide by the total mass to get the position of the center of mass. For a complete ring, you'd expect it to be at the center, and that's what you should find. For half a ring, what is it though? This will tell you how far up that ends up going.